Hello, everyone, and welcome to another discussion of quantum mechanics and physical chemistry. My name is Becker, and today we are going to be discussing the particle in a box. Let's get started. So the one-dimensional particle in a box is a simple application of the Schrödinger equation to a system. It represents a single atom moving in a cube that has impenetrable walls. And based on how we solve this problem, we can apply its concepts to a particle in a 2D and 3D box, boxes where the particle can escape, and eventually real atoms. Now, to create our box with impenetrable walls, we need to set boundary conditions. Our box is going to exist from x equals 0 to x equals a. Our walls are going to be created by having the potential energy be infinite beyond the walls, as we can see right here, but the potential energy will be set to 0 inside the box. This means that outside the box, the wave function is going to be 0, and as a result, the probability of finding the particle outside the box is going to be 0. So we can only find it inside the box, which is exactly what we want. And finally, for continuity's sake, we are going to define the wave function at the boundaries of a box as 0. Great, so with our boundary conditions set up, we can apply them to our Schrödinger equation to solve for the wave function. We're only going to be concerned with the wave function inside the box where the particle exists, that being from x equals 0 to x equals a. So to do this, we are going to keep in mind that we set our potential energy to 0. So V of x is going to equal 0. And as a result, that is going to cross out this term right here. From this, we can rearrange our equation to get this. We just have the second derivative of our wave function, psi of x, is going to equal negative 2m over h. I believe this should be h bar squared times e times psi of x. So from there, we can rewrite our constants as k for simplicity. Basically, k squared is going to equal 2m over h bar squared times e, just like this. And it does seem the textbook is wrong. This should be an h bar. Not sure what's going on there. But anyways, we are left with a differential equation, the second derivative of psi of x over dx squared is going to equal negative k squared times psi of x. So basically, what kind of function can we take two derivatives of with respect to x will give us a negative constant squared times that same function. There's only going to be four possible solutions: e to the ikx, e to the negative ikx, sine kx, and cosine kx. If you're not sure how these could be solutions to this differential equation, I definitely encourage you to just take the two derivatives of each of these, and you will see that this is going to be the case. Now, for simplicity's sake, for solving this equation in further steps, we are going to go with psi of x equals a sine kx plus b cosine kx. This is going to be our most general solution. So, with that, we still have a bunch of constants. We don't know what a is going to be, b is going to be. There's just a lot of unknowns right now. So to help solve for a more concrete wave function, we can apply our boundary conditions. First of all, we can apply x equals 0 in, so we get psi of 0 is going to equal a sine of 0, which this is just going to become 0, plus b cosine 0, which this will become 1. So then we just get b is going to equal 0. So that crosses off this term right here, nice and easy. If we apply our second boundary condition, psi of a equals 0, we can plug this in right here. Psi of a is going to equal a sine of ka, which equals 0. Now, looking at this, you might think, oh, we could just say a equals 0. But if we did that, then our wave function would be undefined for the entire box, meaning our particle cannot exist inside the box, outside the box, it just doesn't exist, which we know is not true. So to actually make this sort of equation work, we can look inside this sine kx. If we want our sine kx to equal 0, then we are going to need ka to equal n pi, n being an integer like 1, 2, 3, and so on, just like that. And if you think about it, I mean, sine of pi is going to be 0, sine of 2 pi is 0, sine of 3 pi is 0, and so on. So this is very helpful. We can rearrange this equation so that k is going to equal n pi over a, and then that is going to give us our new wave function, which actually we can see right down here with this. Psi n of x equals a sine n pi x over a for n equals an integer, 1, 2, 3, 4, and so on. So that's great. But now we need to solve for our a value, and that is where we need to normalize our function. We can use the general equation 1 equals the integral from our boundary conditions 0 to a of psi star x times psi of x dx, and by plugging in our wave function that we had, we get the integral from 0 to a of a star times sine of n pi x over a times a sine of n pi x over a. And we do need to use a trigonomic identity to actually solve this. The solution is in the textbook. We're just going to kind of skip through this. But if we solve this, we get that a is going to equal the square root of 2 over lowercase a. And by plugging this back into our general wave function, we get psi n of x equals square root of 2 over a sine of n pi x over a. And this is going to be our general wave function that is an eigenfunction of our Schrödinger equation. So that's great. Now, using this derived wave function, we can plot it for increasing values of n. As we can see right here, as n increases by 1, a half wave is going to be added to the previous wave function. Here we have one half wave. The wave is going to go, up and then just like that. Now, if we go to n equals 2 from n equals 1, we get an extra half wave right here. And then going up to n equals 3, another half wave, and so on. And as we can see, our particle can only exist in a set of defined states. It can't exist in like some sort of in between. There can't be like 1/4 of a half wave or something, or 1/3 of a wave added. It's always going to be increasing in increments of a half wave. So this has important consequences. These defined states mean that energy is going to be quantized, and we can actually solve for how to calculate our energy. So we utilize the idea that k squared equals 2men over h bar squared, this sort of equation that we had when we were first solving for our wave function. And we can also use the equation k equals n pi over a, what we used when we applied our boundary condition psi of a equals 0. So if we set these equal to each other, first we need to square this, but basically we get n squared pi squared over a squared is going to equal 2men over h bar squared. And by rearranging for this n value, we get that en is going to equal h squared n squared over 8ma squared. Here we just converted our h bar to h using h bar equals h over 2 pi. Otherwise, we can write this as en equals h bar squared n squared pi squared over 2ma squared. It's the same equation, but written just two different ways. So anyways, that is the particle in a one-dimensional box. This concept is used extensively throughout quantum mechanics, so understanding these basic concepts is very important to understanding the later ones. That is going to be all for this video. Thank you all so much for watching, and have a great day!